Okay, so recording is starting. I'll quickly share my screen, and then after that we can get the talks going from people on grants. Okay, so you should be able to see my screen at this point. So I'll quickly go over a few introductory slides. So just for context, this is an update on the zkVM track after what's now been a couple of months of work by the first grantees, and we're gearing up for more work, which I'll talk a bit about later. And obviously, I think the zkVM track will very much be going until the end of the project, because everything in zkVMs will probably be changing until the end of the project and even beyond that. So we're actually looking at these RISC-V zkVMs. RISC-V zkVMs are great because you can take, at least in principle, any program or any Rust program, more specifically most of the time, and try to prove the execution of that program with a zkVM. So you no longer need to write a circuit per program, and instead you have zkVMs that kind of have this built in for you, with obviously the requirement that this takes a lot of effort from the teams building zkVMs. And one trend that does exist in zkVMs is that a lot of them are using RISC-V, which is nice. It's a nice established ISA, and it's probably the closest thing we have to a standard for zkVMs so far, which in some ways is convenient because at least it gives us something to build from, because it's obviously the most basic component of the zkVM and what people actually compile to. There's a lot of issues that come with verifying zkVMs, unsurprisingly, because they're extremely complex. Cryptography in general is pretty complex to implement and to get right. zkVMs are also even more complex than that. And it's incredibly hard to write implementations of zkVMs that are actually fast and also secure. And typically, when you're writing the circuits, you have to make sure that they're very fast and secure, and optimizing for two objectives is usually something that doesn't always work out great. So we've obviously seen that bugs have been found in past implementations. It's fairly likely that there are bugs in current implementations as well. And it would be nice to obviously get these secured before zkVMs start being used. And from the point of the Ethereum and ESM Foundation, we're actually looking at zkVMs within the consensus layer as part of the Beam chain, as well as zkVMs at the layer 1 execution layer as part of native rollups. And that's not even considering people just running other things on zkVMs, including layer 2 rollups, which I suppose native rollups will kind of blend in with. And a big part of the difficulty is that not only is zkVMs complex, there's also no established standards, because this kind of technology is fairly new. The first zkVMs only popped up in the last couple months, couple years for a lot of them, and that comes with a lack of standards. You have different circuit languages. Obviously, you have some circuits that are written in Rust. RISC-0 has their circuits written in Zergen. There are a ton of other circuit DSLs going around. You also have different arithmetizations, which obviously relate to the circuit, but it means that obviously Jolt has circuits written in Rust, but the circuits obviously look nothing like the air circuits from Plonky Street-based zkVMs and so on. And to some extent, you even have different RISC-V targets when it comes to actually compiling things to there, and in particular with respect to the zkVMs. Most of them now are running the kind of RV32IM RISC-V specification. Some of them have started running the RV64IM specification, so going from 32 bits to 64 bits. And some of the RISC-V zkVMs, I'm thinking of SP1 in particular, also run other kind of customizations with respect to their implementation of RISC-V, and that to some extent comes with RISC-V being a modular ISO. And then the obvious big other challenge is that because this is fairly new technology and there are no established standards, things are constantly changing. You have fairly frequent small changes, things like new precompiles, optimizations to the circuit, and things like this. And you also have big changes, which can be essentially complete rewrites to accommodate new proof systems. And this means that when you're trying to verify zkVMs, one big challenge is obviously to actually verify something before it changes and having to do it all over again. And specifically for us, this means trying to come up with either ways of finding better ways of embedding form verification in the development process is suddenly something like, automatically formally verified precompiles would be fantastic, and hopefully we get close to that over the next year or two, and ideally just actually get kind of fast precompiles that are automatically formally verified. And there's been some kind of early work in that direction, at least as far as automatically generating precompiles, if not formally verifying them. And we'll try and contribute on the full verification side. But also it means that for the bigger changes, when people do what are essentially complete rewrites for new proof systems, or whether people go from a 32-bit RISC-V circuit to a 64-bit RISC-V circuit and kind of have a big rewrite because of that, it'll be important to be able to hopefully support these changes and make sure that we're definitely not slowing down the development of zkVMs, and hopefully even maybe helping make them get more performant, because a lot of the time what happens is when you do try to formally verify something is that you end up with the ability to find optimizations, and suddenly some of the past papers that have come out on formally verifying things like circuits to find optimizations, and I'm thinking of one recent effort with zkVMs, which is the paper on verifying the Jolt-ish optimization to the Kwong, Carl, and Justin Saylor did at X16Z, I think reduced the size of some of the lookup tables by, I think it's maybe 87.5% and things like this for some of the lookups. And so there's also a bit of scope to actually help the development of zkVMs through that, and to make some of these changes potentially even better, or to actually contribute some of these small changes without breaking things. So when it comes to actually formally verifying zkVMs, the current approach is essentially to take more standards we can. And at this moment, that's essentially the official Sail RISC-V model. Is more or less the only thing that we can have as a standard. There will be some work that will be presented in a few minutes here on adding a Lean backend for the Sail RISC-V model, which has kind of had amazing progress and is very much on the way to being useful. And obviously, you also have the existing Sail backends for Rocq, Isabelle, and Hall 4. Which we can hopefully make use of as well when we do work with other proof assistants. But other than that, for the most part, I think at least to start with, we've just been experimenting with different approaches. One approach is obviously to extract, Rust or circuits written in any DSL to any kind of proof assistant and try and prove things correct in there. The downside of this is obviously that it's something that happens subsequent to any kind of circuit being written, and obviously is maybe a bit further away from trying to embed ourselves into the development process and being able to help out with the development process as is happening. And it also means that if you're waiting for things to be written to actually get to formally verifying them, if you then take a couple of months to formally verify them, but then these things are rewritten by the time you're done, it quickly becomes inefficient, and it's very hard to scale this thing out to the multiple zkVMs we have. I think going back to the first slide, you have the kind of table of all the zkVMs. You have pretty close to 20 zkVMs in total, definitely over 10 RISC-V zkVMs. And this means that we need to experiment if only to find an approach that actually scales to be able to handle all of these. So one other approach is obviously to just think of what's a better way to write circuits, and one of these approaches can be to just write circuits, and as part of writing them, proving the circuit correct in a proof assistant itself. And so that obviously is a very strong embedding for verification in your development process. The experimental part here is figuring out whether we can write circuits that are obviously performant enough, and also to compare the time it takes to write a circuit in this manner and proving it correct, compared to the time it might take to write a circuit in Rust or another common DSL. And we'll hear a bit more about this approach from zkSecurity in a few minutes as well. And then the other experiment that we can do is obviously to think, we're not going to change the way that people are going to write their circuits, because they're attached to the development process. They're focused on shipping quickly because they're operating in quite a highly competitive environment where it's important for them to show that they're constantly pushing performance at least as well as any other competitor. And so something that we can do then is to actually think, people write circuits however they want. What we'll do instead is have a intermediate representation for circuits which can provide basically a unified layer from which we can deal with circuits that come from different high-level languages, or that are written for different arithmetizations. And this is essentially, to some extent, about scaling out the approach of extracting circuits to proof assistance, which is mentioned a bit above this and which I just talked about. Because some of the workload goes on to obviously having the different high-level languages point towards that IR. And the developers of those high-level languages can kind of do that and take a load off of the form verification teams that might otherwise be writing the code to extract, a circuit from Rust or another DSL to proof assistant. But also it allows us to build reusable tooling, whether that's any kind of analysis tool, which can also be automated with SMT solvers, but also to take a lot of circuits from different high-level languages, get them into the IR, and then write an extraction from that IR to a proof assistant and have a common representation for many more circuits in that way. And Veridise has been working on an MLIR dialect, and we'll hear a bit about this from them as well. And so the key thing at this point, because things are still changing, and I think we will be verifying circuits to make sure that what we do actually works. But I also don't expect any circuits that we verify or any precompiles, even that we verify to kind of still exist in a year or two, the way things are going. And so a lot of this is really trying to figure out possible common abstractions and ways to develop more or less general purpose proof infrastructure in proof assistance. And this could mean finding ways to represent circuits in a kind of nice, convenient way, finding and developing tactics that allow us to prove things about circuits much more efficiently. Obviously building, better automation, making better use of SMT solvers, or developing obviously kind of new procedures for SMT solvers as part of that, and essentially trying to make sure that at the end of the day, no matter how people write circuits, no matter what the choice of developers is in their way to write circuits, we can either deal with that, or obviously just offer a better alternative, which could obviously be something like just running circuits in Lean, or something like this, and finding better ways to maybe match fairly simple specifications for circuits that are not performant but easy to prove things about, to obviously more heavily optimized implementations, and trying to maybe link these two and see if that helps out. So we've got several active grants, which I've more or less mentioned at this point. The main active grants are basically, we've got a grant to the University of Cambridge, LIndy Labs and Galois, who've been working on a Lean backend for Sail, which has had fantastic progress. Galois is also working on lookups and essentially Jolt circuits in Lean, and being able to kind of prove these correct down the road. We've got zkSecurity, who are experimenting with writing air circuits directly in Lean, which is going well, and I think has shown a lot of interesting things in terms of how to think about circuits and how to think about writing circuits, and how to then have nice composable proofs about these circuits from proofs about subcircuits, and getting these done in a nice way, which will be, I think, useful down the road just to write circuits in Lean itself, but might also be adaptable to circuits that are then extracted into Lean, and we'll reconvene once there's a bit more work there to see what we can do about that. And then we also have Veridise, who's been developing an MLIR dialect of circuits that's been progressing well, and getting to the end of the first stage of their development, which means that we'll be open sourcing this IR fairly soon. And as it gets more established, we can obviously support more high-level languages to compile down to the IR, but also start taking requests and trying to support features that people would find useful for automated analysis at the IR level, but also in terms of extracting that MLIR dialect into proof assistance, Lean Rocq, and whatnot. And we'll maybe hear a bit about this as well. And we also have a bunch of upcoming work that's already planned, which is essentially at the paperwork stage. And so I'm hopefully not jinxing myself by talking about it now. And we'll hear bits about this from the people who are going to be doing this work. And so we've got a lot of plans, obviously, around Plonky-3. Plonky-3 is, I think, the most widely used proof systems in RISC-V zkVMs at the moment, even if it's obviously not the only one. And so we'll be putting some effort into there, both in Lean and in Rocq, to try and provide a basis to offer as much coverage as we can, especially because obviously different RISC-V zkVMs that are using Plonky-3 might be operating on different forks of Plonky-3. And so we're not looking at a simple, unique set of artifacts, but potentially kind of many more. And so it'll be important to try and scale this out and find out how much we can scale this out for a given proof system and different instantiations of this. We've also got obviously some upcoming work on hopefully developing better tactics in Rocq, based off of CertiK's experiments of working on their verification effort of zkWASM earlier on. And that's hopefully something that will make subsequent efforts of that kind much more easier. And also some experiments with Verus, which is a tool for Rust verification and can be maybe a good way to offload some of the proof obligations that can be handled by automation with a tool like Verus, and keep the more difficult things that can't be handled as automation to a proof assistant, but to try and speed things up and to make life a bit more easier, especially as SMT solvers can always improve as well. So I'll stop there. I'll stop there for now, but then I'll obviously pass off the microphone, I guess, to the different grantees first, and then we'll have some short introductions to some of the upcoming work by the people who are going to be doing that. And so we'll start, I think, in the order that's on the slide there. So we'll first have James from Galois will talk a bit about both the Lean backend for Sail and their efforts on Jolt circuits in Lean. Then we'll get obviously someone from zkSecurity. I think Marco will talk about their efforts in writing circuits in Lean. And we'll also have Veridise with Sankara talking about their work on the MLIR dialect, which I think they've called LLZK. And then we'll have a few short talks about the upcoming work. And so, yeah, I guess whenever you're ready, James, you can go for it.
Okay. Can everyone see this?
Yep.
Okay. Yeah, so hi, I'm James. I'm a researcher at Galois, and we've been working on verifying the Jolt zkVM. And this has been in collaboration with the team here at Galois and LIndy Labs, Cambridge, and Edinburgh. So I think Alex covered the motivation pretty well, so I'll skip over this. Basically, we want to verify the Jolt zkVM. And so I guess at least in my opinion, Jolt is one of the most promising zkVMs, at least according to our internal benchmarks. It has 5 times faster proofing times than RISC-0 on CPU. It emulates the RISC-V 32-bit machine, and it's under development by Michael, Sam, Arisu, Srinivath, and Justin. And maybe Jolt is a bit unique from other zkVMs. Its statements are represented in R1CS. It uses lookup tables, and then it composes lookup tables to make larger lookup tables. So this is sort of the long-term goal of what we're trying to prove. These are like sort of the statements of correctness that, at least how we see them today. So basically, the first theorem is saying that if the witness is well-formed, the circuit, if it's not well-formed, then the circuit will reject it. So like maybe the witness has bogus field values that don't actually correspond to machine words. So in that case, the circuit should obviously reject it. And then the second theorem is saying that if the witness is well-formed, then the circuit should be satisfied if and only if the inputs and outputs correspond to the underlying reference RISC-V model. And yeah, here's a visual representation of sort of the same statements. You can see up top, you have like the witness values of the inputs and the outputs, and these are field elements. And then there's some concretize function that maps them into machine words. And then you want to make sure that these correspond to each other. So here's our high-level approach of how we're planning to do this. In stage 1, which is currently in progress, we are implementing a Lean backend for Sail, and this will give us and hopefully others a reference RISC-V semantics so that you can prove equivalence to. For the second part, we are implementing a DSL for specifying ZK statements in Lean. We're calling this library zkLean. Right now, we're focusing on Jolt-style statements, but in theory, it should be generalizable to most styles of zk statements. And then we're also implementing a tool that extracts Jolt's arithmetizations into zkLean. Eventually, we want to prove the previous statement that I showed, and then we'd like to integrate these proofs, these Lean proofs, into Jolt CI so that Jolt can continue to be verified as it evolves. So here's a little bit of background on Sail. It's a dependently typed DSL for defining instruction set architectures. It provides models for ARM, x86, RISC-V. It's been around for a while now, and these are pretty well-tested models, so there's good confidence that they're correct. The nice thing about Sail is that there's backends for many different theorem provers, like Isabelle, Hall, and Coq. So then you can, if you want to prove properties about these models, you can extract them to those languages and then use them in your proofs. Here's a little excerpt of what Sail looks like. This is from the RISC-V model. And here, this is the XOR instruction. You can see how it defines a mapping for how to extract. This is the XOR instruction that I'm running. These are the registers, etc. And then it's a pretty nice functional style language where you can do pattern matching on the instruction type, read from the registers, and write the result back. And yeah, it's pretty nice language. It's dependently typed, so it uses an SMT solver to check things like bit vector lengths, that kind of thing. So you get some more assurances of correctness. And like I mentioned, in our project, we're building a Lean backend for Sail. So this will allow us to extract sales models into Lean. So for us and maybe others on this call, this will give us the RISC-V semantics in Lean. And then for others, if you want to use sales ISA models in Lean, this will allow you to do that. And we're doing this in collaboration with Cambridge and LIndy labs. So we've made a lot of good progress, but maybe I wanted to just maybe highlight some of the challenges that we've run into in implementing this backend. So one of the things is that there are no pattern guards in Lean. So if you look at the Sail instruction at the top, this is the load instruction, but then in Sail, you can define these pattern guards, right? So this pattern guard only applies when this condition is true. But there's no way to natively express this in Lean. So what this has required us to do is you have to basically expand out a bunch of nested pattern matches when this happens. And it does cause a little bit of a blow up. So we're looking at ways to reduce this size in the output semantics. So another challenge that we've run into is that Lean's type system has struggled a bit for unifying dependent integers. So you can see at the top, you have a function bar that takes a 32-bit vec. And then when you append it to itself, it should be pretty obvious that it's a 64-bit vec that satisfies foo. But yeah, I guess Lean's type system isn't able to do this by itself right now. So we've had to do a few things to work around this so that it actually compiles in Lean. So we've done things like adding manual coercions, and then we've had to sometimes add wrapper functions around operations like bitVec.append. So here's the current status. The RISC-V model that we're generating right now, it's much larger than I would expect but it's 100,000 lines. I think most of it's in the encode and the decode functions because you have a lot of those nested pattern matches. Right now we're down to 4 errors, but I think there's a root cause of only one case due to mutation happening inside of while loops, and we're working on almost fixing that. So hopefully we shall have the whole model compiling soon. Obviously, since these RISC-V semantics are a reference, we want to make sure that they're correct. So we're rigorously testing them using the Spike test suite and other RISC-V tests. We're doing some differential, like property-based testing to make sure that the RISC-V semantics are correct, and we're integrating all these tests into Sail CI. So yeah, we can make sure that it stays correct over time. So zkLean is a library we're developing for encoding zk statements. So our primary goal here is it should be amenable to verification, and it should be automatically extractable from front ends. Initially, we're focused on Jolt style statements. So this means R1CS, lookup tables, and composition of lookup tables. And we're designing it so that it should be extensible so that other features and constraint systems can be added in the future. And again, we're agnostic to the style of zk backend, so error or whatever should be fine. Here's a small example of like what zkLean looks like today. This is subject to change, obviously. But yeah, I guess maybe a few things to highlight is that we have this circuit builder. It's a monadic. It's called zk builder, and it gives you various functions. Like you can create a new witness variable. So here you're defining a new witness variable x. You can see x is a circuit variable that's polymorphic over the underlying field f. And then you can also do things like constrain that variable to some Boolean expression. So here we're saying that x is 0 or 1. And then you can return a reference to x if you want to reference it or assign its value later. So a big part of Jolt is subtables. So this is how we encode subtables in zkLean. So Jolt defines subtables by providing their multilinear extension function. These are typically over inputs of size 2 to the 8. And here you can see we're defining a subtable from a multilinear extension. This is the eq subtable. So you can see these constraints I'm showing here are basically saying the first bit of each argument has to be either 0 or 1, or both have to be either 0 or 1. And then you do the same thing for all 8 bits for the arguments. So this is like the 2 to the 8th size input subtable of equality check. Now to make larger lookup tables, Jolt combines these subtables. So it basically breaks up the inputs. So in this case, these are 32-bit inputs into chunks of size, I believe there are 4 chunks of size 8. And basically, you're saying apply the eq subtable to each of these chunks, and then you need to provide a function to combine those results. So here you're just multiplying each of the subtable results, and this gives you the overall lookup table result. Okay, so now that we have zkLean, we want to actually extract Jolt circuits, but Jolt implements these circuits in Rust. So what we've been doing is we're implementing a tool that automatically extracts Jolt circuits into zkLean. We have a Rust binary that links Jolt as a library. It extracts the AST representation of the circuits, and then it outputs Lean files in using this zkLean library. So just to give a sense of what this looks like, at the top, this is the Rust code for the eq subtable. Yeah, it's just encoding what we showed previously. And then you can see our tool will extract this, extract the AST, and then build this Lean function at the bottom that builds the subtable type and yeah, and we can use it and prove properties about it. I guess maybe one thing to highlight is that we did notice or identify like a small performance optimization. So when we extracted this truncate overflow subtable, this looked a little funny to us since it always returns 0, which basically means it's not necessary. So at least for 32 bits and 64 bits. So we were actually able to remove this, and this gave actually a modest prover runtime improvement of about 2%. So our long-term goal here is we want to integrate with CI. So our tool, yeah, we want to ensure that Jolt stays compliant with the Sail specification as the code base evolves. So we want to be able to automatically extract the statements even as fields change, maybe the lookup tables change. Jolt is actually planning to update its lookup table arguments and its constraints. So this will be a real test to see how well things work. And but we expect that the system will continue to work even as those changes occur. Yeah, and in the long term, maybe these Lean proofs will continue to work even without human intervention. Maybe they can be automatically repaired using AI techniques, but this is definitely long-term future. So here's a summary of what we're doing. We take Jolt's circuits, which are in Rust. We have an extractor that extracts them into Lean in our library called zkLean. Then we have the RISC-V model in Sail. We're using the Lean backend that we're implementing. And then eventually we aim to prove equivalence between these two representations in Lean. Yeah, so that's it. I guess, Alex, are we doing questions now, or?
If anyone has questions, now's a good time. And otherwise, we can always return to that after other people have given their talk.
I just had a quick question. So this is Sankara. So I was just wondering how this relates to the kind of previous efforts that went on with Carl Quan and stuff to do this kind of verification. Are you, yeah, like what kind of thing? What is it? The same scope, or yeah? Maybe you can talk a little bit about that.
Sure. Yeah. So I think Kwang's here actually. Maybe I saw him join, but my understanding is that.
In the chats.
Okay. Yeah, my understanding is that that effort was just focused on the lookup table arguments, but it did not really involve like the R1CS or the memory. So we're aiming to prove the entire equivalence of the full RISC-V semantics versus just the lookup tables of the individual instructions.
Okay, thank you.
Mm-hmm.
Okay, so if there aren't any other questions for now, then we can move on to zkSecurity's work on writing air circuits in Lean.
Yep. Can you see the slides?
Yeah.
Yep. All right. So hello, everyone. I'm Giorgio from zkSecurity, and we'll briefly talk about Clean, which is a Lean embedded DSL for writing zk circuits. So our goal is to write circuits directly in Lean. And the idea is that we tightly pack circuits definition with their assumptions on their inputs, specifications, and the proof of correctness. And our framework, let's say, focuses on modularity of the circuits, and of course usability. And the idea is that then we can export circuits to a concrete proof system. That is to say, like a Rust proof system. And specifically, we target AIR, arithmetization, and we assume to have a low-level table lookup primitive available by the proof system. Right, so this is the main object of the framework. It's called formal circuits. And it's a packing of the circuit definition, which is the input-output shapes, and then the constraints and lookup, so the wiring, let's say, and the constraints that are defined in the circuits, together with assumptions on the inputs and the specification, and then soundness proof and completeness proofs. So let's see, what do we mean by soundness and completeness? So soundness is that for all possible assignment of the witness, so for all possible assignment of the variables, so in the, let's say, adversarial case, where the witness is arbitrary, if the assumptions on the inputs are satisfied, and the constraints and the lookups are satisfied, then the specification is satisfied. And the completeness is kind of the opposite direction. So the completeness is saying that we can emit a valid proof for every input, so that the honest prover is able to generate a valid witness that satisfies the constraints. And so these two theorems, let's say, gives us the assurance that the circuit is not either under constraint for the soundness and not over constraint for the completeness. Right, and one of the main points, let's say, to solve about this this framework is composability, right? So, for example, here I've depicted like one circuit that uses some subcircuits which have already proofs of correctness, right? And we want to somehow use the subproofs of correctness to write the proof for the overall circuit. And we kind of are able to do it by basically lifting the subcircuits to a formula, which is basically assumptions imply specifications, right? So if in the greater proof, if we are able to satisfy the input assumptions of the subcircuit, we can basically give take the proposition of the specification of the subcircuit, which only relates input and outputs. And then the nice thing is that we do not care about whatever is going on in the subcircuit. We only care about the specification, so it's a relation between inputs and outputs. So for example, if I have a CertiK subcircuit, I don't care about whatever is going on in the subcircuit. I just care that it's computing the CertiK function. And this is what formal circuit looks like in Lean. So it's a structure parameterized by some f, which is our field, and it has some beta and alpha, which are type maps, and implement provable type. So provable type is just a way to say that beta and alpha are isomorphic to a vector, so it's just a bunch of structured elements. And then we have the main, so it's the main circuit, definition, assumptions on the inputs, specification, soundness and completeness proofs. And for technical reasons, we also have this other lemma, but it's usually automatically proved by REFL. So it's just there to say that we are not doing any strange things in the circuits. Right, so one example on how this is working. So let's say we want to implement a circuit which computes 8-bit addition. So one interesting fact is that we can encode assumptions on the prime. So for example, here we are encoding that P is large enough. So it's P is greater than 512. Then we can define input and output shapes. So in this case, it's two structures. And this is 8-bit addition, like full adder style. So it takes in carry input and carry output. The assumption on the input is that X and Y are bytes, and that carry in is a bit. And the specification we want to prove is that Z is equal to X plus Y plus carry in modulo 256. And the carry out is the integer division of x plus y plus carry in by 256. And this is what actually defining the circuit looks like. So it's we also use this a kind of similar monadic approach. So it's a circuit monad which returns outputs, and here we are doing a witness. So a witness basically introduces in the context a variable, and we also give a function which is the honest prover witness generation, which is only used in the completeness proof. And then we do a byte lookup on Z. So we are doing basically a range check. And then we witness another variable, which is carry out. We do an assertion, and this is kind of interesting because this assertion primitives basically allows us to instantiate the Boolean.circuits subcircuits, and then in the proof we can lift to the specification. In this case, it's quite simple because I mean the Boolean circuit is just checking that the input is Boolean, but in the proof it's lifted to the fact that carry out is either 0 or 1. And then assert 0 is just a primitive to add a new constraint. So we are asserting that this expression is 0. So a few things about concrete AIR arithmetizations. So this kind of structure is somewhat arithmetization independent, right? We are just working over variables and polynomial constraints and lookups. And we instantiate concretely over AIR tables, or let's say AIR traces, by providing a mapping from abstract variable to concrete trace cells. And for technical reasons, we do not actually allow to encode every possible constraint that is possible over AIR traces, and specifically we disallow wrapping around. So, for example, if there is a constraint that references the next row, it can only be applied to every row except the last, because if it is applied on the last, it will wrap around. And this gives us a very nice, very well-behaved inductive structure so that we can do inductive proofs over traces. Right. So if we, the main template is that we have a boundary constraint on the first row and an inductive constraint over 2 rows. So it references the current row and the next row. And if this inductive constraint is applied to every row except the last, then we can infer like an inductive property about the trace. And of course, the same composability principles apply. So we can lift every subcircuit we use to their specifications. Right. So a bit of what's next, what is planned with this framework. So of course, adding more gadgets to actually make it usable, such as addition, bitwise AND, XOR, rotations, and so on. And build formally verified Ketchak and Blake circuits with this idea that we can compose larger and larger circuits. And then we want to build a formally verified minimal VM to showcase that it's possible to formally verify, let's say, real world things. And then, of course, the goal will be to implement a real world VM, which covers a subset of RISC-V, and maybe in the future even the whole RISC-V instruction set. And of course, one last note is that it's open source, so you can take a look. All right, if there are any questions, we're happy to answer them.
Yeah, if there are no questions, maybe one or two comments from me as well. So I'm working together with Giorgio on this. So maybe one thing to mention also is we also had quite a few challenges for the last few months. Specifically, the hardest thing I think for us was to that sometimes we just hit scaling walls where like we hit points where if our circuit was like a bit too big, then it became really hard to make proofs about it, because like the monad we had written down no longer resolved to like the low level data structures. Like so, and we went through a couple of iterations with this. Like one thing was just simplifying our core structures such that they resolved faster. But the final point where we thought it doesn't scale, Giorgio had the idea that we just because Lean has like built-in monad functionality, and before we were just defining our own monad, and then we switched over to the built-in state monad, and that suddenly made it much faster. So that was an interesting learning. We had to change a couple of things because our thing wasn't a plain state monad. It had some additional property, but we were able to work around that. So that was an interesting finding. And now, I think now my hypothesis is that we are at the point where we have seen that we can define fairly large circuits and have them simplify. And also with the composability, I think the size of circuit that we even need is kind of limited, because if it we can build up large circuits from a couple of small ones. So I think at this point we kind of think it will work for any project, for any circuit project. Yeah.
Well, I have a quick question. This is Sankara. So how do you find, like, have you started writing proofs for the circuits or generating proofs? Like, is it mostly automatic at this point, or proofs, or is it how much do you have to write manually?
Yeah, that's a good question.
Let's say 99% manually.
It's yeah, 99% manual.
But I'd
Yeah,
say it's like having obviously inspected some of the proofs for some of the grant deliverables, the proofs don't look as bad as I thought they would originally.
Do you think SMT solver support would be helpful in the effort? Like, do you think there's enough support, or do you think more would be helpful?
I can say the first thing that would be useful would be automating. So in these proofs, there are usually two parts. One is just simplifying the statement to simplifying the whole machinery that we build to an actual mathematical statement. And then the second part is like just proving the mathematical statement, like something about two equations or three equations in a finite field. And that's the second part is kind of fun. So I think definitely automation would help in this part, but the first part is like not as intuitive for someone who doesn't know a framework, like reducing the statements to something simpler. And so that's where we definitely want to add more automation, like a tactic that reduces this part of it reduces the constraints, and then another tactic that
Some kind of optimization
introduces the witness generators and so on. So yeah.
I see. Oh.
And then, so I think, as Giorgio said, the code is open source on GitHub. There's a 32-bit addition circuit in there that has proofs for it, which is, I think, for now, is like the best one that looks like, a real circuit that actually does something interesting and has a proof for it. And yeah, CertiK and so on will be following soon.
Yeah, and we tend to write the proofs right away. I think it's a fairly natural process. Like you're writing the circuit, then you're also writing the proof for it. Yeah.
Yeah, Marco, you've got a question?
Yeah, I wanted to ask if you did any optimization, even very simple things, like, I don't know, inlining or stuff like that.
So we don't have any like automatic optimization on the constraints. We write the raw low-level constraints directly, the constraints and the lookups. Yeah, I mean, I think the framework principle is that I think that could happen, but it would happen at a completely different level, right? So
okay, so you write the constraints that are already sort of optimized by hand.
Yeah.
Okay.
I think that
they have the good properties that you expect.
Yeah. So my thinking is that you can really be aggressive with not using a lot of constraints, because you're afterwards proving that it's correct anyway. So you don't have to be too defensive.
No, it's just that there are some optimizations that are very, I feel they're very hard to do by hand, in the sense that like you have this big circuit, there are a bunch of, for example, expressions that maybe are shared, and like, and they're also non-local things. Like maybe you have a subcircuit that is perfectly optimal and another one that is perfectly optimal.
Yeah.
But then you put them together and they do share some stuff, and you will not notice by hand. So
I agree. So a pass like that just removes like duplicate constraints or something, that could also be interesting at some point.
Okay.
Yeah. And there's something nice as well, I think, about being able to have even an optimized spec that was a nice proof for it, because then if you do apply a bunch of optimizations and you can get back the optimized circuit in a similar representation, it becomes a bit easier to match both circuits and to get a proof from that, rather than obviously trying to get a proof for a heavily optimized circuit with no kind of reference and optimized version for it. But then figuring out how to do that and how to get these optimization passes in is would be kind of interesting future work. And the even more interesting thing would obviously be to have optimization passes sort of verified to be correct and preserve the semantics of the circuit and whatnot, which is kind of doable, right? If you look at the literature on like CertiK and other verified compilers, you can verify these things. It's just quite intensive in terms of work. And obviously, deriving automated optimizations and verifying them at the same time would be the ideal case that we can work towards.
Maybe one final thought that regarding how general this framework is. So we kind of designed it to represent error circuits. So it has like expressions and lookups, like polynomial expressions and lookups. But then at some point we realized that like Plonk, the custom gates in Plonk can also kind of be seen as lookups. Like they have the same interface. I think it's just it's just like an abstract thing that verifies some relation, and it has a bunch of inputs. So I think it kind of naturally extends it, because in R you will say that there are certain lookup tables available, and similarly in Plonk you will say that there are certain custom gates available that you use. And then R1CS is just polynomial constraints. So I think it kind of encompasses everything.
Yeah, but I think this is the general point about lookups, right? And with Jolt especially, the idea was that if you're only doing lookups, your optimization doesn't have to be very expressive, and it becomes very simple. And then at that point, like all our optimizations kind of blur with each other because they just end up being as simple as possible. So yeah, I mean, hopefully everyone converges to just doing lookups and life becomes easy. But we'll see how that goes. Okay, I think we'll pass it on to Sankara to talk about their work on a MLIR dialect for circuits and everything, I guess, that has to do with SMT solvers as well, since that's their expertise.
Okay, yeah, hi. Let me make sure I can actually share the screen. Yeah, let me go here. So can you see the presentation here?
Yeah.
And if I hit start, you can still see it?
Yeah.
Okay. Yeah. Hi, everybody. I'm Sankara. I'm at Veridise, and I'll talk a bit today about our work building out LLZK, which is going to be this IR for zkCircuit languages. And this is like one of the brand projects, as you know. So to give a little bit of motivation, Alex talked a bit about this too, but as you know, there's a number of different languages out there for writing zk circuits. Some of them are like these DSL, some of them are embedded DSLs. And I think that's pretty great because we want to have a lot of different ways to write circuits. But I think the problem is that right now, a lot of these languages have basically are building out an entire compiler stack. And so as a result, I think what we've seen is a lot of fragmentation. So some languages only support certain arithmetizations. There's also limited kind of applicability of a lot of security tooling, like some tools only work on Halo 2, some work on CertiK, some work on maybe a subset of them. And so I think, and then some have like various certain optimizations that others don't. So I think we just, lose a lot of the kind of development and insights that we've seen across the different languages by having these kind of separate compiler stacks. And I think in the real world, what we have are IRs like LLVM, where a lot of high-level languages are basically compiling down to this IR. And we have a lot of shared infrastructure as a result of that. And so we're proposing doing something similar by building this language LLZK. And so the idea here with LLZK is that you would have the languages develop sort of front ends essentially for compiling down to LLZK. We call it lower level, but actually you'll see it's a little bit high level as well. And then LLZK, we can develop like different dialects, transformations, optimization passes, and then we can build, different backend transformations to support different arithmetizations. And we can also build security tooling on top of this language so that we can get support for multiple languages essentially for free. And so we are not the first, obviously, to propose doing an IR. There have been different IRs designed for circuit languages in the past. And so LLZK is kind of inspired by some of those. But essentially, one of the goals that we wanted to do is build on top of some sort of robust compiler infrastructure. And so we decided to go with MLIR. So it's really easy to build like analysis passes, transformations, optimizations. It has good diagnostic information, which I think is super important for any compiler. Has a reasonably accessible tech stack. It took a little bit to kind of get ramped up onto using MLIR, but I think now it's very easy to develop and there's like a good community for support. And MLIR is naturally like extensible, so you can build different dialects. And so that could be very useful in the context of zkIR. We can create different dialects for proof systems, maybe that have certain use cases in mind, or so on and so forth. It's also wanted to, as like the other talks here have discussed, we wanted to be so backend agnostic. So the IR is going to essentially allow people to define polynomial constraints and lookups, but essentially not tie to either like Planck or R1CS. We wanted the IR to be able to also express circuits in a modular fashion. I think that's useful for identifying optimizations. It's also useful for tooling, security tooling. We can like exploit the modularity. We wanted the IR to also support witness generation and constraints. And the reason is like we have built a lot of static analysis tools that are able to find bugs in circuits by kind of exploiting discrepancies between the witness generation and constraints. So having that, I think, would be useful to security tooling. And then we wanted to design the IR so that it's easy for front ends to be able to essentially transpile a circuit DSL into our IR. So that way we can kind of easily reason about the correctness of the different translations from one language down to our IR, and it should be easy to add new languages. And I'm not going to go into a huge amount of detail about the actual base dialect that we have in LLZK, but you can kind of see from this example. So on the right is like LLZK, and then on the left is like a CirCom program. And so there's like a fairly good correspondence between structures in, like, for example, CirCom, and as you'll see in like Zergen, and kind of core constructs in LLZK. We also have a witness generation encapsulated within a certain compute function as well, and then constraints emitted within the constraint function. And then we have we will have the ability to also do like product programs, so you can between the computation and the constraints for more extensive like verification. And so right now I'll just talk a bit about like the deliverables that we had and like where we are in terms of our progress so far. So there were about 5 or so deliverables. We're about 3/5 of the way through. Right now we've defined the ODS for LLZK, which is just basically all the instructions in LLZK. We've defined those in MLIR now. We've started building up a good like analysis framework for doing static analysis like bug detection, also for optimization. So some of the analysis stuff that we've developed we built out a constraint dependency graph, which the compiler can use to quickly detect, let's say, unconstrained signals. We also have a new interval analysis tailored for finite field reasoning, which I'm pretty excited about, because like we have some of our internal tools use it, and it's very easy to, like, we can use that interval analysis to prove determinism for like non-trivial circuits. We've also implemented certain circuit transformation passes, like so LLZK has templates similar to CirCom, so you can do template instantiation, loop unrolling, and flattening. And we found MLIR was pretty useful in this respect because we can kind of reuse that existing infrastructure. And we're currently in the process of implementing circuit optimization. So one is delinearization, which I think will be useful in R1CS. For R1CS backends, we also are doing this redundant constraint elimination. So I think, as Marco mentioned, essentially there's going to be cases where certain constraints might be, where circuits might be implemented with some amount of redundancy, maybe to make it easier to check correctness. And so then a redundant constraint elimination pass can go through and remove constraints when we can prove that they've already been generated. So that's like in progress right now. We're also targeting Zergen as the initial front end. So Zergen is a circuit DSL that was written by RISC-V, and it's intended to be general purpose. It's kind of used to write their V2 circuit. And so it's also, Zergen's compiler infrastructure is also in MLIR, so it's very convenient for us. So we can, without too much effort, start writing a front end for Zergen, and then we're starting to implement like multiple backends. But the one where I think R1CS is a pretty easy target to get things rolling, so we're just going to implement an R1CS backend as a first step. So that's also in progress, and we have a lot of things we also want to do on top of this so far. After we finish the basic deliverables, we want to add obviously more front ends. So we have a CirCom to LLVM front end and a GNARC to LLVM front end, so we can adapt those to basically transpile to LLZK. We want to also add more backends, so we could also target another backend IR, which is something we're thinking about, like Polygon's PIL. And then we also maybe want to have a Plunky 3 backend for Starks, which I think would be useful. We also, in parallel, want to do some LZK to Lean extraction, which Alex talked about. I think there's this like Lean MLIR framework that's out there that we can try to build on top, which already has some infrastructure set up to do this extraction. And I think that would be useful. We could also get basically the ability to prove correctness about LZK circuits for in conjunction with all the other work that's been discussed here. I'm also excited to try to do verified optimizations and transformations. I think that's really important, being able to sort of prove that all the optimizations we actually perform in LLZK are sound. And I think, that's kind of a non-trivial effort. But I think it would be good to start with like maybe some simple optimizations, prove their soundness, and then have like a pipeline for being able to, prove the correctness of these things as we add new optimizations. And I also think like LZK should be a good IR for people to also build their own verification tools. So, and I think automated verification is kind of our, as a company, expertise. So being able to do things like these verification condition generation, having support for weakest precondition, strongest postcondition transformers, and invariant synthesis, I think that would be very useful for being able to do proof automation. So yeah, so those are just some of the directions. We're obviously open to discussion and see whatever the community sort of, we're gonna basically open source LZK very soon. I think maybe mid to late April is probably good. We want to have basically an end-to-end product running, basically being able to take something from a high-level source language and then being able to generate like a prover and verifier, show how you can run LZK's optimization passes, how you can use and write analysis in a programmatic way, I think would be great. So we want to just, and then also documentation. So once we have that, I think we'd be comfortable open sourcing it. But obviously, if you want to look at the source code beforehand and discuss, we're happy to share that with the people on the call. So so this is the basic summary of what we've done so far, and then I'm happy to take questions.
Okay, so if there are no immediate questions, then we can have a quick introduction to some of the upcoming work, and then we can, right after that, we can have maybe a broader discussion and see where we're heading in the future. So like I said a bit earlier, something that's obviously in the plans is some Plonky3 related work, which is the paperwork is in process. But we have both some efforts in Rocq. So Guillaume from Formaland will be working on being able to extract Plonky3 circuits into Rocq so that it can be proven correct there. And Nethermind also has some plans for adding a bit to Plonky3 itself, and then in order to facilitate extracting Plonky3 circuits to Lean, and also being able to prove these correct. And a lot of this is really because Plonky3 is obviously the most used proof system at the moment, and so it's a good opportunity to try and scale out efforts across multiple proof assistants to try and support that. And that will also be, in some sense, a bit of an experiment in seeing whether we can find good ways to help each other out despite using different proof assistants. So I'll let Nethermind and Guillaume talk about this in a second. The other thing that's in the works is that CertiK have previously done some great work on applying form verification to the zkWASM zkVM, and that's allowed them to also identify tactics that could be useful to add to Rocq in order to handle obviously modular arithmetic and packed integers. So they'll be doing a bit of work on this, and they'll also be evaluating and experimenting with using Verus as a tool for both circuits and EVM precompilers, which will give us maybe a bit of a sense of how much we can maybe make our lives a bit simpler with tools like Verus. There are other tools as well, like Hacks, of course, and a few others out there for Rust specifically, and figuring out where the boundary is between maybe using these tools and using proof assistance for harder things. And maybe for context, I can say that obviously, much like Hacks has a backend for Rocq, Verus may in the future have backends for things like Lean or something else. So yeah, I think we can do it in the order of maybe Guillaume, Nethermind, and then CertiK, and then after that we can discuss things more broadly.
Yes. Yeah, thanks. Yes, I do not have a slide. our plan is to use our Rocq of Rust tool that translate Rust code to Rocq.
So we can't see your screen yet.
Yeah, I do not have
Okay, so
to use Rocq of Rust to translate the AIR library of Plonky3 to the proof assistant Rocq, and to apply it to the CACAC example that is in the Plonky3 library, and some examples of SP1 circuits, check if it actually works. And after we want to define a monad also to represent the circuits by taking inspiration from the current works. I've done experiments with CIRCOM for this monad to be able to plug our translation from the Rust implementation to this monad, where it should be simpler to reason. And hopefully we can also synchronize with a static team who has more experience in the verification for in Rocq. So we'll focus more on the translation from the implementation to Rocq, and try to synchronize with the CertiK for the verification work.
Cool, thank you. And yeah, whoever from Nethermind, I guess Julian is still sick, but I see a few other people from Nethermind here, so someone might be able to talk a bit about that. If not, I can talk about it as well.
No, I think it's okay. Fabrizio and I can talk a little bit about it. Yes, Julian is still ill. I am definitely following suit. So we are hoping to develop an infrastructure in Lean that would allow us to verify Plonky3 circuits in a modular way. So we're hoping to design an interface for sort of an external tool communication between like for Plonky3, and then use it to extract the constraints and chip boundaries into Lean. We are sort of basing that on lookup and permutation arguments, and then we also will verify a number of examples. I think that our latest target are Blake and CatchHack, but I'm not 100% sure on that. Perhaps Fabrizio can give more detail, because I'm quite high level on this.
I can say actually what it will be.
Oh, yes,
I think the choice as proof of concept was this, like CatchHack or Blake's tree. I have these two in mind after talking to Daniel, who obviously develops Plonky3. So it'll be either of these two. Potentially, if we're looking at CatchHack in Rocq, we might do Blake's tree in Lean, or we could do the same one to compare both results. But yeah, it'll be one of these two.
Yes, just to say separately, we are going to very soon have a verified CatchHack in Halo 2. So perhaps some of that will transfer, some of it will not, but we'll see.
Yeah. Okay, thanks a lot. And then we can let I guess Vilhelm from CertiK will be talking a bit about their plans.
So yeah, a very quick update here. So we have been awarded 2 grants, which we will start working on very soon now. One of them is about tactics for Rocq proofs, and one of them is SMT-based proof. So both of them built on previous work. So in the last year, we did this verification of the zkWASM, the zkVM, which we used in Rocq. And then in addition, we also did a different project where we verified part of an Linux kernel using an SMT-based proof called Verus. So that's kind of relevant because most of the work in the zkVM space is done in Rust. So like our conclusion from all of this is that probably in the future there will be like a hybrid. If things are written in Rust and are doing interesting things in Rust, then we might want to use like a system like Verus that's good at Rust, but we might also want to use interactive theorem provers like Rocq and Lean. And like the balance of it is unclear. It depends on like what's most efficient. So both of these grants are sort of exploring where the boundary is, I believe. So the first grant is to improve the Rocq proofs. So actually in our zkVM development, we left 2 gaps. We didn't prove some of the arithmetic modular operations. We just did that informally in pen and paper. And secondly, we didn't do the instruction decoding. Both of these are because we thought they're simple and unlikely to have bugs, but they're very fiddly and annoying to do given the current Rocq standard library and tactics. So like the right way to do this should be to exploit some properties of zkVMs in general. Like in particular, in a zkVM circuit, we know that things are representing like 64-bit integers or 32-bit integers. So like somewhere in zkWASM, there's one constraint saying that if you shift and add together these values, they're equal to that value. And the constraint says this, but actually when we axiomatized it, we just dropped the mod field order. And like our informal argument why this is fine is that we know that these are 64-bit integers, so there's no way this addition can be higher than the field order. But ideally, we want this to be formalized. So we want some automatic tactics that can use this type of information to prove that the addition doesn't overflow and that it is safe to like ignore the overflow possibility. And the same also holds for the instruction decoding, like proving these injectivity lemmas, saying that if you shift things and add them together, it's kind of fiddly if you do it step by step in Rocq, but it should be possible to automate it. So the goal here is to make some reusable tactics that are sort of suited to this math that comes up a lot in zkVMs. And the other grant is about trying to do something in SMT solver, and that's also motivated by our zkWASM experience. So we had a bunch of lemmas like this, saying that you can commute the and or operations, and these took like hundreds of lines of proof in Rocq to prove, but we noticed that the Z3 have theories that can prove them automatically. So that sort of raises the question, how much easier would this be if we were using an SMT-based system instead? So for the grant in particular, we will take like a small part of zkWASM and also the corresponding small part of SP1 and try to redo like those proofs using Verus instead. So in particular, we'll focus on like the byte and bitwise parts, which is around 460 lines in both systems. So by doing these proofs for both zkWASM and SP1, we will get some sense of like, does this result generalize or is it just specific to zkWASM? And by doing zkWASM, we can directly compare against the Rocq proofs. So like similar to what we did with zkWASM, we will like manually translate the code into pure Rust and then prove the pure Rust code. And that sort of ties into our idea of like hybrid verification. Like it should be done in the future. Things should be done in 2 steps. Like first prove the functional correctness of the circuit construction code with respect to pure implementation, and then prove the pure implementation. And we will start working on this very soon. So hopefully we'll have some progress in the next meeting.
Thank you, and thanks to everyone who else who talked before this. I think, yeah, if anyone has questions or comments they want to bring up after all of this, then now is a good time. And otherwise, I think I have, I guess, potentially a few things to say, but I'll let anyone else comment first.
Yes, I had a question for you, Vilhelm. So do you think it's possible to connect Z3 to Rocq, for example, to have less reasonings?
I mean, you mean connected with Lean or with Rocq? I guess so. Like there is some existing work on tying SMT solvers, but like step 1 is to try to use it to prove something and see if it's actually faster or not.
Yeah, I think on the Lean side, there's Lean SMT, and there's been a lot of work going on trying to improve support for SMTs in Lean. I'm not too sure what the status of that is in Rocq, and obviously Isabel was maybe the gold standard for that, and we'll see if anything from that end kind of ports over. And I think similarly in Lean, there's probably some Sledgehammer version of Lean is coming at some point. It's been in the works for quite a while. And yeah, so I think I'll there are a few thoughts that I have basically after all of this and looking at the kind of progress that we have now, which is essentially that I think we're getting close to showing that you can kind of take any zkVM and probably prove it correct. And I don't think that was necessarily in doubt before, but we're also getting kind of much better estimates of how long it takes to do this kind of work, and that means that we can actually compare it against the rate of development of these zkVMs. And the next steps, I think, as I said a bit in my introductory talk, is that obviously is figuring out how to make the gap between verification and development as small as possible. James obviously mentioned, trying to integrate their work into Jolt CI. We had similar observations yesterday on the EVM track about trying to integrate things into CI. And I think with better automation, better use of SMT solvers and better tactics in all the proof assistance, I think it always get quite close to this. And the other thing is obviously that because, like I said, there's been a few instances of when you try to formally verify some things, you find optimizations, and you also maybe find ways to automate optimizations and to be able to reason about them a bit better. I'm fairly hopeful that we can figure out how to maybe bridge the gap between development and writing circuits with kind of verifying them. And obviously kind of zkSecurity's work is the closest thing going in that direction. And it'll be interesting, obviously, once we progress to see kind of how how we can benchmark this and how we can integrate this with everything else. And obviously there's the IR work, which will hopefully help unify everything together. And so yes, I'm fairly hopeful that the status quo of circuit verification will improve quite a bit and especially become much more flexible, both because we get a better sense and a better set of tools to verify things, but also because the way that people are writing circuits maybe become simpler to verify. I think obviously things that are written with lookups have much simpler responsorizations, simpler constraints, and obviously also if you look at the Jolt code base in particular, far fewer constraints than I think previous generations of circuits that didn't have lookups did, because these could sometimes have kind of fairly insane amounts of constraints. And there are, I think, stories from the Nethermind side of trying to unfold Halo 2 circuits in Lean and Lean just crashing because they would run out of memory. But yeah, so I think we've got progress. We've got significant process going on, but I still think there's quite a bit of progress to do it, to work on. And I think as the projects we've heard about today progress and get towards the end of their planned work, the big next step in within a few months will be to kind of look at things and try to figure out where we can hopefully unify things. So we've seen, for example, 2 examples of circuits in Lean, based on the Jolt circuits, and for the zkSecurity writing circuits in Lean, we also have Plonky 3 circuits getting it extracted into Lean, and all of these to some extent have some differences in them, both in the way that they're written and their responsorialization and the way that they're used. But at the same time, I think if you think of things like lookups, it should hopefully be possible to try to formalize some lookups and then provide a kind of nice way to use proofs that follows from these formalizations of lookups, regardless of the underlying responsorialization. And then if you only end up with fairly simple constraints from the use of lookups, try to build better tactics and automation and essentially have kind of well-developed proof infrastructure in Lean, definitely, and then hopefully also then extending that to Rocq and potentially other proof assistance as well, if need be, because at least for the short term, I don't foresee zkVMs converging towards something stable. I think even if it's the multiple zkVMs using Plonky 3, they still look, pretty different at the end of the day. And you have a couple active forks of Plonky 3 at this point as a result. So yeah, I'm hoping that when we regroup again in a bit of time, obviously a lot of the work that's been mentioned today will be finished. We'll be also then thinking about the next steps, and one of these next steps will definitely be to try and think about how to unify and find common ground on how to represent circuits, how to deal with circuits, and therefore also being able to develop tooling that can be highly specific, but also fits, a lot of circuits if they're represented in the same way. So I think that's my main thought, and then obviously there'll keep being new arithmetizations. I think obviously with Phineas, you have kind of M3 and things like this. So they'll be staying on the lookout for new things, but hopefully as things improve on the development side as well, they'll also become easier on the verification side, despite kind of changes and introducing new arithmetizations and things like this. So I think that's the main way I'm looking at things at the moment, is mainly along these lines of trying to unify things and hopefully get the best of each project that's going on now unified in a couple weeks, couple months, and going from there later on. And then also, so there'll be one base task is also at the moment we're developing what is primarily tooling, and there are many circuits that we're obviously not looking at actively. The next big thing will be that once we do have this tooling developed and that we feel like we've made progress on the tooling side, it'll be scaling out the effort to verify a lot of circuits and to establish how to verify circuits, so that also there's somewhat of an industry standard for any zkVM team that wants their circuit verified to know exactly what they should ask for and what they should expect, both in terms of who can do the kind of work, but also in terms of somewhat of a standard of work and kind of cost and timeline and things like this, and getting kind of the cost and time required to verify any zkVM circuit down by as much as possible, I think will be obviously what makes this project a success or not, so that we hopefully, like I said, get to a stage where we're not slowing down development of zkVMs, or not requiring them to be slow in order to verify them, but actually potentially even helping them accelerate and speed up their performance. And so so if there are no other comments, we can end it here. Obviously, we're well past the hour, and we'll have the cryptography track update will be next Wednesday at 5 p.m. UTC as well, and then we'll have another one of these series of track updates later on, late spring, early summer, once a lot of the work is done from the work that's ongoing and the work that's about to start. So yeah, I'll stop the recording now.